In this video, we'll discuss the chi-squared test, which is a actually pretty darn useful and clever test that a lot of students don't always appreciate the utility of. So we'll talk a little bit about it and talk about where it can be most useful. So there's two kinds of chi-squared tests, the test of independence and the goodness of fit test. The test of independence looks at the relationship between two or more variables and determines if they're independent from one another. The goodness of fit test compares to a fixed set of values and determines if the fixed set of values is the same or different than what we actually observe. So the goodness of fit is kind of like the one sample version of a chi-square test, and then the test of independence is like a two sample test, though it's not really samples in the same way that the two sample t-test was, where you have two different groups. In chi-squared, it's more about the number of variables. So chi-squared is used with a categorical independent variable and a categorical dependent variable. And again, with the test of independence, we can actually do multiple, though we'll just stick with two variables, an independent and a dependent variable. So an example of this situation is like, let's say, your political affiliation. So your political affiliation, you could be Republican, Democrat, Libertarian, anarchist. I mean, you could be a whole ton of different things, right? Green Party, there's a whole bunch of parties I'd never even heard of before. So what you can tell about this is that all of these are just categories that you can fall into, that you can't really rank them, and certainly there's not an equal distance in any meaningful way between them. So your political affiliation would classically be considered as a categorical variable. And we can determine if this is related to whether you voted in the last election. So did you vote in the last election, yes or no? That also is just categories that you can fall into. It's important to note here that unlike with the t-test, remember in the t-test, our categorical independent variable had to just have two groups. In the chi-squared test, either of these categorical variables can have as many groups as you want. So as I mentioned, like political affiliation, that does not just have two groups. That can have a whole bunch of different groups. The limiting factor here is not going to be on the number of groups. It's going to be, you want to make sure that you have at least a certain amount of data points within each cell of your table. So speaking of tables, data that we can analyze for a chi-squared, because both variables are categorical, can be stored in what we call a contingency table. So you've got a certain number of columns and a certain number of rows, and then this would be like variable 1 and variable 2. So let's say that we had political affiliation. So we had Republican, Democrat, and Libertarian. Actually, you know what? When I was in high school, there was a person who was a member of the Marijuana Party. So we're going to have Republican, Democrat, and the Marijuana Party, just for fun. And then, did you vote in the last election? We'll have yes, no, and I don't remember. So what would happen here is that when we ask people, we'll ask, okay, what's your political affiliation, Republican, Democrat, or Marijuana Party? And then we'll ask, okay, well, what is your, did you vote in the last election? Yes, no, I don't remember. And so we'll have a number in each of these cells in the table, in this contingency table, that's the number of people. So in this case, this first one would be the number of Republicans who voted in the last election. This would be the number of members of the Marijuana Party who did not vote in the last election. And this cell would be the number of members of the Democratic Party that don't remember if they voted in the last election. So that would be how you would sort one of these tables in a contingency table, and what I mean by the numbers in each cell. So when we have the different variables, we can have as many as we want. The rule is you have to have a certain number of values in each cell, and the expected number of 5, it kind of depends on your situation as to what those numbers is, but typically you want to make sure it's not 0, that your expected values are at least 5 is a classic way of looking at that. So the hypothesis for this particular test is a little different. The null hypothesis is that there's no association between the variables. And the alternative hypothesis is that there is an association between the variables. Notice that this isn't, I'm just going to say it isn't written in the same way. And it's because what we're looking at is an association. There isn't really a measure of association that we kind of have that's easy to write in a simple equation format. You can write this out. It just is much less meaningful than in the ways that we typically do. So I should say you can write this out mathematically or in a mathematical formula. It's not quite as informative or intuitive. It's not as meaningful as, frankly, just writing out the sentence. So we're looking at association or no association between the variables. And I should, of course, mention, as with all of these, correlation isn't causation. So that's not what we're talking about. We will touch on that later in the course, too. So our test statistic, well, this is a chi-squared test. So we're going to have a chi-squared test statistic. We have O minus E squared divided by E. So this is the observed value of the cell minus the expected value of the cell divided by the expected value of the cell. And this is distributed as a chi-square distribution. The degrees of freedom are going to be the number of rows minus 1 times the number of columns minus 1. And our critical value will have x squared distributed as a chi-squared with this many degrees of freedom. And of course, if we're looking for the critical value, we'd have 1 minus alpha over 2 for a two-tailed, or 1 minus alpha for a one-tailed. Now we tend to only, this is something that we only test typically in a single direction, so do be aware of that. Now I should mention what's R and what's C. R is the number of categories in the row, and C is the number of categories in the column. So in the previous example, you know, how many political parties do you have? Well, that's the number of columns. How many options to the question, how many answer options to the question, did you vote in the last election, do you have? Well, that would be the number of rows. All right, and for the decision, I mean, the decision is just the same as last time. We find the critical region, and if the test statistic is in the critical region, then we reject the null. And if if p is less than alpha, if we're using the p-value approach, then we reject the null. If not, we fail to reject the null, and that's kind of it. I mean, it's not any more complicated than it was with our t-distribution. The only change is that the critical value has changed. I will say that one of the reasons people like the p-value approach is that while the critical value changes, you know, t-test, it was a t-distribution, chi-square test, it was a chi-square distribution, so you use different critical values to, or tables of numbers to find the critical region. The p-value approach doesn't change. It is interpreted pretty much the same throughout, no matter what statistic you're using. So it is one reason that people prefer the p-value approach to the critical value approach, but both are useful and important to know. In the next video, we'll kind of continue our review of statistical tests that you should already know with a discussion of correlation.